start with the next topic, which is matrix 2. Here I am not writing, I will just write the necessary part because everything is written here and it will be helpful for all of you. So first of all, this is the chapter where we will discuss the eigenvalues and eigenvector. These eigenvalues and eigenvectors have a very important role in many mathematical fields, also the physical fields. Where the zero space occur, this eigenvalue and eigenvectors actually plays a very important role. I am taking one page here to describe it fast, then we can go for the notes. There are so many pages. Okay, so what the eigenvalues and eigenvector is, if you take a matrix A, suppose a matrix A is given and which is a square matrix. So a square matrix A is given. Now if you can find one non-zero vector x, so this is a non-zero column vector or non-zero vector. So this is a non-zero vector. So if you can find a non-zero vector x for that A in a way that this will gives you lambda into that x. This lambda is a real value or complex value, whatever may be. This lambda may be real or complex. So, but this is a value, this is a constant, means this is a scalar. This is a scalar value, and into that same vector, if you can find this type of x, then this value lambda is called the eigenvalue, and this capital X, this non-zero vector, is called the eigenvector. Now if I give one example, then it will be more clear to you. Like if you take the 2 3 1 4, this is a 2 cross 2 matrix. Now if I multiply this with a vector, so this is your capital A, if I multiply this by the vector capital X, which is 1 1, let it be 1 1. So I have multiplied the matrix by the vector. Now after the calculation, what you are getting, just calculate it. So this is equal to, so 2 into 1, that means 2, plus 3 into 1, 2 plus 3, this is 1, plus 4 into 1, 4, that means you are getting 5 5. So now if you take the 5 common, you are getting 1 1. That means after Ax, this x is again unchanged and you are getting some lambda here, some constant value here, and into the x again, x vector again. Now if such type of representation is possible for a matrix, then we say it will not always possible, but if such type of arrangement comes, that if you can find such x which is giving you Ax equal to some lambda x, then this lambda is called the eigenvalue, and this capital X, which is a non-zero vector, it is called the eigenvector. 0 will never be eigenvector because eigenvector is always a non-zero vector. So always remember this, the zero vector is never be eigenvector. Why? Because if we allow the zero vector in that matrix 2 3 1 4, then if we put it to the 0, in that case you will get 0 0. Now 0 0 can be represented as 5 into 0 0, 0 0 can be represented as 6 into 0 0, 7 into 0 0, whatever may be. That means all these values will be then eigenvalues, but it is not possible. Corresponding to one eigenvector, you will always get only one eigenvalues, not more than that. That means corresponding to this 1 1 eigenvector, you will get only one eigenvalues, like this 5, only one. That's why 0 0 is not allowed for the eigenvector. Eigenvector is always a non-zero vector. So now you know that eigenvector is non-zero vector, and another thing what you know is that corresponding to an eigenvector, there is only one eigenvalues, not more than that eigenvalue. Then corresponding to an eigenvector, there is only one eigenvalue. But is the converse true? That means, can we say that corresponding to corresponding to one eigenvalue only one eigenvector is there. Vector is there. Can we say that? This is another question. Corresponding to one eigenvalue. Corresponding to one eigenvector, there is only one eigenvalue. We have already said that, and this is a true statement always. But corresponding to one eigenvalue, only one eigenvector is there. Can we say that? Now, look with another example. The same matrix. I have taken the same matrix 2, 3, 1, 4 and I have multiplied the matrix by 2, 2. Now I am taking the x vector as 2, 2, not 1, 1. Now what you are getting? 2, 2, 4 plus 3, 2, 6, 3, 4, 6, 4, 10 and this is 2 plus 8, it is also 10. Now take the 5 again outside and you are getting 2, 2. Now you can say that corresponding to this matrix 5 is the, so this is Ax and this is lambda x. Now lambda is again 5. That means eigenvalue is again 5. But eigenvector changed. Eigenvector is now 2, 2. Not only why 2, 2, if we give a 3, 3, that means 2, 3, 1, 4. If I give the 3, 3 here, then also you will see that it will be 3, 2, 5 and 9, 15. This is 6, 9, 15 and this is also 3 plus 12, 15. If you take the 5 here, again you will get the 3, 3. So 5 is again the eigenvalue, but the eigenvector is 3, 3. So this eigenvector is not unique type of thing. This eigenvector is like a infinite type of solution. That means anything which is multiplied k times to that 3, 3, that is another eigenvector to it. That means I am saying not only that 1, 1, if we get 2, 3, 1, 4 into kk, like as you have seen the solution in the solution in the infinite cases, if we take the kk, then you will get this is 2k plus 3k means 5k and this is also 5k and you are getting 5 into kk. That means 5 is one eigenvalue and kk is eigenvector corresponding to that. So not only the 1, 1, anything k multiplied by 1, 1 is also eigenvector to that eigenvalue 5. So eigenvector is nothing but this is just the solution of this system of equation, because this is a system of equation, na? Whatever I have written here, this is just a system of equation. And what is the system of equation? The system of equation you can follow from here. I have written that Ax equal to lambda x. So A matrix is 2, 1, 3, 4. X matrix can be, I don't know what is x, so I have taken this as x1, x2. Lambda I don't know, so I have taken this lambda and x matrix is x1, x2. Now this lambda matrix can be written as lambda into 1, 0, 0, 1 into x1, x2. I think everyone will agree with me, because after multiplying this form you will get actually x1, x2 again, because 1 into x1, 0 into x2, it will be x1, and 0 into x1, 1 into x2, it will be x2. Why I have taken like this? Just because the left hand side is a 2 cross 2 matrix and the right hand side is a 2 cross 1 matrix. So I can subtract it from there. It is a matrix and it is just a constant. I can subtract a matrix from a constant or constant from a matrix. That's why I have made it like a matrix. So now multiply the lambda with that, you will get a lambda 0, 0 lambda. And then there will be x1, x2. Now the left hand side and right hand side looks like same. So it is a 2, 3, 1, 4 and x1, x2. Now I can subtract it. Now after the subtract, actually we will get 2, 3, 1, 4. Then minus, it is lambda 0, 0 lambda. And if we, and then outside it will be x1, x2, and left side you will get only a 0 vector. Because nothing is there, I have taken everything on the left hand side, so right hand side will give you a 0 vector. So now after the, listen, you will get 2 minus lambda, it is 3, it is 1, it is 4 minus lambda, and here you are getting x1, x2, and this value is equal to 0, 0. So this is nothing but, this is a system of equation 2 minus lambda x1 plus 3x2, this is equal to 0, then 1x1 and plus 4 minus lambda into x2 is equal to 0. Now eigenvalue, eigenvector x1, x2 is nothing but it is just the infinite solution of that system of equation, and you know that infinite solution comes when rank of this matrix is less than 2, because this is a homogeneous system, and in a homogeneous system if the rank value is equal to 2, now this is a homogeneous system. This is a homogeneous system, and in a homogeneous system if rank value is equal to 2, that means if both these rows are non-zero, rank 2 means number of unknown is 2, number of unknown is also 2, and rank number of unknown 2 means it has unique solution, and unique solution in a homogeneous means it is the trivial solution, and trivial solution means x1 is equal to 0 and x2 is equal to 0. That means it is the 0, 0 vector, and you all know it will never be an eigenvector. It will not an eigenvector. So eigenvector, if this system has an eigenvector, it will not permit that the rank will be 2. For this system, if eigenvector comes, then its rank should be less than 2. That means its rank should be less than 1. So one row should be 0 row. That means for eigenvalue, for eigenvector, we are getting that rank value should be less than what? 2. And if rank of the left side matrix is less than 2, that means determinant of this should be non-zero? No. Determinant should be 0. Am I correct? Rank less than 2 means determinant should be 0, na? Now tell me, am I correct or not here? That I am claiming that rank value is less than 2. If the rank less than 2, can I say that the determinant value is 0? If you have any doubt, you can also ask me. That's why I am taking that. It is a very confusing state, but you should have to understand that. Otherwise, it will be difficult to continue the eigenvalue, eigenvector part. If you have any doubt, ask that why I am saying rank less than 2 means determinant 0. And if you understand that, then tell me, okay, sir, I got it.
Yes, sir.
Okay. So, everything is got there. Because if determinant is non-zero, then you have a 2 cross 2 minor, which is non-vanishing. That means rank is 2. Since I am saying rank less than 2, that means obviously there is no 2 cross 2 minor which will gives you non-zero value. That's why we are taking the 1 cross 1 minor. So that means determinant value can be taken as 0. Now when determinant is 0, you will get the eigenvector. So just take the determinant 0, 2 minus lambda 3, 1, 4 minus lambda, this is equal to 0. You will get that 4 to 8 minus 6 lambda plus lambda square minus 3, that is equal to 0. That means lambda square minus 6 lambda plus 5 is equal to 0. So lambda minus 5 into lambda minus 1 is equal to 0. That means lambda is equal to 1 and lambda is equal to 5. So these two are the eigenvalues of the system. That means by taking the rank determinant value 0, whatever you are getting, that lambda is equal to 1 and lambda is equal to 5, these two are the eigenvalues of the system. And as you can see, we have taken 1 here. The eigenvalue is actually 5, we have taken 1. Another eigenvalue this system has, and the eigenvalue is 1 actually. So doing the determinant 0 will gives you the eigenvalue. Now after putting the eigenvalue here, if you put the eigenvalue here, suppose lambda is equal to 1 if you put here. So put it here. So 2 minus 1, that means 1, it will be x1 plus 3x2, that will be 0, and x1 plus, if you take the lambda is equal to 1 here, it will be again 3x2, that will be 0. Obviously one equation will depend on other, because rank is 1, rank is not 2. If rank is 2, both the equations are useful. That's why the infinite solution case is very important. That since here rank is equal to 1, we are taking rank value is equal to what? 1. Rank 1 means one equation will be dependent on the others. So you can neglect one equation, and this only one equation is useful for calculating the solution, not the both equation. So only one equation you can use for the solution, as I have already said at the previous actual discussion, that here rank is 1, so one independent equation is there, another is dependent. So just neglect the dependent equation and take the independent equation. So I am taking the first equation or the second, both are same here. So neglect one equation and take another equation. Now from that equation, if you can calculate, so rank is what? Rank is 1. So rank 1 means nullity value is what? Nullity value is 2 minus 1, it is 1, because 2 is the number of unknown. So number of unknown minus rank will give you nullity, and nullity 1 means you are now free to take one variable as k. So now let us take that 3 value, take that x2 is equal to k. I have taken x2 is equal to k. So x2 is equal to k means what is x1 or x1 k now? Let x1 is equal to k. No, x2 k is better, otherwise fraction will come. Fraction is also okay, but we are avoiding the fraction. Let x2 is equal to k. So in that case x1 will be minus 3x2, that means minus 3k. So we are getting x1 x2 is equal to minus 3k k. So take the k common and minus 3 1. As I said that k multiple of minus 3 1 is a solution. So this minus 3 1 can be taken as a eigenvector. And not only that minus 3 1, any k multiple of that minus 3 1 is another eigenvector. So eigenvector is never unique. Eigenvector is always you will get it as an infinite number of solution. So that's why infinite number of solution case is important. Eigenvector are just the solution of this homogeneous system. Solution of the homogeneous system. Now from the solution you can see how many independent vectors are there? Only one. Corresponding to lambda is equal to 1, you are getting the eigenvector as minus 3 1 as an independent vector. All the other vectors are k multiple of that, so they are all dependent. Only one independent vector there, it is minus 3 and 1. So corresponding to lambda 1, the system of equation a minus lambda I x equal to 0, what you have taken here, whatever we have done here, it is a is equal to lambda x. In the next line, what we have done? In the next line, we have done ax equal to, this is ax equal to lambda x. Then lambda x is written as lambda identity x. Now this is ax equal to lambda identity x. Then left side a minus lambda identity x, this is equal to 0 matrix. This is that line. A minus lambda I x equal to 0. Then we have taken that for the infinite solution, determinant of a minus lambda I is equal to 0. Now from the determinant of a minus lambda I 0, we have calculated the lambda, and then after putting the value of lambda from this system of equation a minus lambda I is equal to 0, from this system a minus lambda I x equal to 0, if you put the value of lambda is equal to 1, suppose lambda is equal to 1, that means you are getting a minus identity x equal to 0. If you solve this homogeneous system, since rank is equal to 1, you will get an infinite number of solution, and the solution is actually x equal to k into minus 3 1. And this is the independent part, and this independent part is actually forming the basis for the solution space. So actually this is a solution space, not a solution only. Solution means one point. It is actually a family of point. Family of point means it is a space. Now if you take this solution space, in this solution space you can see only one independent vector there, and that means here the nullity value is 1. That's why I have says that nullity is nothing but, nullity is the dimension of the solution space of the homogeneous equation, and this is the homogeneous equation. That means nullity is the dimension of the homogeneous solution space of this a minus ix equal to 0. So whenever now you think about the nullity, so now it will be clicked in your mind. That means how many independent vectors you are getting corresponding to that lambda is equal to 1. Nah. So corresponding to lambda is equal to 1, you are getting one independent vector. So that is called the nullity corresponding to that A minus I matrix. Why I am saying that? Now if you put this lambda is equal to 5, if you put lambda is equal to 5, just put it here. So if you put lambda is equal to 5 in this equation, lambda is equal to 5. So what you are getting? So put it here 5. So 2 minus 5 means minus 3x1. Then plus 3x2, this is equal to 0, and if you put 5 here, it will be 5x, it will be x1, and then plus 4 minus 5 means minus, so minus x2 is equal to 0. Now in these two equations, you can see the first equation is just minus 3 multiple of the second. So you can neglect any one of the equations. So for calculation simplicity, I am neglecting the first one and I am taking the only second one, because rank is 1, so nullity is 1. I can take only one equation and one variable independently. So let's take x2 is equal to k, or x2 is equal to something k dash. In that case, x1 is also equal to x2, which is k dash. That means you are getting the solution x1 x2 as k dash k dash. That means it is just k dash into 1 1. That's why I have taken 1 1 as an eigenvector at the starting. But here now we are calculating it by using the rule that lambda is equal to 5 is giving you the eigenvector 1 1, but for starting we have taken is as 1 1, but actual process is calculating like that. First calculate the determinant of this 0, then you will get the eigenvector, and here only one eigenvector is there which is independent for lambda is equal to 5. So actually 1 1 vector is producing the eigenspace for lambda is equal to 5. It is producing the eigenspace. So just if it is little bit confusing, forget everything from here. I will again discuss it in the class. It is not very much easy thing to understand all of this eigenspace actually a concept, but for now I think you know that why we are taking the determinant of A minus lambda is equal to 0. This is I think now clear, that why we have to take A minus lambda is equal to 0 for calculating the eigenvector, because without that, if you don't take the determinant equal to 0, in that case rank will be 2, and if rank 2, then both the solution will be a 0 solution, and 0 solution will not give you a eigenvector, because eigenvector are always a non-zero vector. So for a homogeneous system, if you want a non-zero solution, for a homogeneous system, if you need a non-zero solution, that means a non-trivial solution, so your rank should be less than the number of unknown. That means the determinant value should be 0. It is a singular case. So that's why our primary criteria is to taking the determinant value equal to 0, then calculate the value of lambda, then solve the system of equation. I will take only one problem and take 4 to 5 minutes just to illustrate. If in exam it will comes how to do the process of this, just only for one problem, and then I will leave the class. So from our practice set, I am taking one problem how the question actually looks like. So suppose a question is given like this. I'm cutting the question, it will be easy. So question number, this is 1, desktop 6. Okay. So this will be the question. It is question number 25. Find the eigenvalues and the eigenvector for the matrix. This is the case. This is the given matrix. Now this is your A. So your A value is here. I don't know what is the vector, so I have taken x is the eigenvector and lambda is the eigenvalue. So Ax will be lambda x. Now lambda x can be written as lambda identity x. Now that means A minus lambda identity x will be 0. So this is the homogeneous system. So we have to build the homogeneous system here. So that means if lambda and is the eigenvalue and x is the eigenvector, your A vector 5 4 1 2, your A minus lambda I, this matrix, if we just note down this matrix, it will be looks like, or suppose if you write the A minus lambda I here, so how it looks like? A matrix is that minus lambda into identity matrix is 1 0 0 1, that means 5 4 1 2, and then minus lambda 0 0 lambda. After the subtraction, it will be 5 minus lambda, 4 1 and 2 minus lambda. This will be the matrix, and your system is actually looks like, you don't have to write all these things, this is just for rough calculation, I am showing that, but in exam you have to do all these things. So it is 5 minus lambda 4 1 2 minus lambda, and then here you are getting x1 x2, this is equal to some 0 0. Now this is the system of equation, and from this system of equation you need a non-zero solution. A non-zero solution you need, and for the non-zero solution this rank of the system should be less than 2, and rank should be less than 2 means the determinant of this part 5 minus lambda, that means this A minus lambda I, this should be 0, otherwise you will get a zero solution. Now we will make that determinant of A minus lambda I, this is equal to 0. So for eigenvector, so for eigenvector you are getting, or you can say that for non-zero solution, whatever may be, for non-zero solution your determinant should be equal to 0. That means it is 5 minus lambda 4 1 and 2 minus lambda, and this value is equal to 0. Now calculate the determinant, it will be 5 minus lambda into 2 minus lambda, then minus 4, this value is equal to 0, that means it is 10 minus 7 lambda, then plus lambda square minus 4 is equal to 0, or it will be 5 4 1 2, so it will be lambda square minus 7 lambda minus 7 lambda and plus 6 is equal to 0. So you are getting 6 and 1, so it will be lambda minus 6 into lambda minus 1, this is equal to 0. That means you are getting lambda is equal to 6 and lambda is equal to 1. So these two are the eigenvalues. So lambda is, since it is a 2 cross 2 equation, so for a 2 cross 2 equation 2 eigenvalues will be there. For a 3 cross 3 equation 3 eigenvalues will be there. It is not a guarantee that you will get always a real eigenvalue. You may get a complex eigenvalue also. But for now, if you are getting some real eigenvalues, now corresponding to lambda is equal to 6 and lambda is equal to 1, we will solve the system of equation. Now we need this equation for the solution. We need this equation. So actually the system is 5 minus lambda, then 1, then 4 and 2 minus lambda into the x1 x2. This is equal to 0 0. This is the system. That means it is 5 minus lambda x1 plus 4x2 is equal to 0. This is first system. Second system is x1 and plus 2 minus lambda into x2, that value is equal to 0. These two are the system of equation. Now calculate it. Just simply put the value of, so for first we start with lambda is equal to 6. For lambda is equal to 6, we calculate the eigenvector first. For lambda is equal to 6, put the values of lambda here. So put it here, lambda is equal to 6. So 5 minus 6 means minus 1. So minus x1, then plus 4x2, that value is equal to 0. And the second equation is x1, then minus 4x2, this is equal to 0. As you can see, both of these equations are actually same equation, just one minus multiplication is there. And also rank of the matrix is 1 here, so rank is equal to 1 here. So nullity value is also 1 here. So only one equation we will take, another equation we don't consider. And in this equation we can take one variable as a k. So let x2 is equal to k. Let take x2 is equal to k. That means x1 value is equal to 4x2. So x1 is equal to 4k. So that means you are getting that solution x1 x2, this is equal to 4k comma 4kk. So you can take the k common, so you are getting 4 1. That means anything k multiple, anything multiple of that 4 1 is also another eigenvector. So that's why eigenvector are not unique corresponding to eigenvalue. So now we can say that eigenvalue 6 and eigenvector is equal to 4 1, and it is not a unique one, it is one eigenvector, and other eigenvector are k multiple of that 4 1, and eigenvectors are never unique. So eigenvector are not unique because it is coming from an infinite solution. So how it will be unique? It will be always in infinite nature. Infinite number of eigenvectors are there corresponding to one eigenvalue. Now similarly, for lambda is equal to 1 also you have to do the same thing. Now put lambda is equal to 1 in that system of equation, and what you are getting? For lambda is equal to 2, you are getting 4x1 then plus 4x2, this is equal to 0, and if you put x1 value is equal to 1 here, so it is x1, 2 minus 1 is 1, it will be x2 is equal to 0. So it is the another one. Now here also, since rank value is equal to 1, one equation will be dependent on the other. I am neglecting the first equation because it is the 4 multiple of the second, and I am nullity is also here 1. So I can take one dependent variable as a k. So I am taking that. So it will be okay. So if you take k1 here, because we have to take 2 times it, so take it k1, and k1. So it will be k1 into that. Now for the second case, I am taking it at k2. So let x2 is equal to k2. Then x1 value is equal to minus x2. That means minus k2. Hence the solution is x1 x2, and that is equal to x1 is minus k2, and here it is k2. Take that k2 common, you will get minus 1 1. Now anything multiple of minus 1 1 is actually eigenvector of the eigenvalue lambda is equal to 1. So now we can say that the eigenvalue is 1 and eigenvector is minus 1 1. So it is one eigenvector only one. But others are the k2 multiple of that, and where this k2 is actually belongs to z, any integer value, that is actually k2, and here also k1 is also belongs to z, any integer value you can take, any positive value, negative value, or any, but this is not equal to what? 0. Always remember that very clearly, that it is z except the value what? 0. Here also it is z except the value 0, because if you give k1 is equal to 0 and k2 is equal to 0, then the whole term will vanish and the eigenvector will be 0 0, and it is not permissible. So k1 value is any non-zero value belongs to the z, and it will gives you the another eigenvector. So this is the process of finding the eigenvalue and eigenvector. So this is the process. So if any other matrix is given, then you can follow this process to find the eigenvector. In our practice set, some questions are there where you can practice it, like question number 24 and 26. So it will be your homework. I will give that. So question number 24 and 26, finding the eigenvalue and the eigenvector. So you can do it just by following this solution. And the question that we have arranged here, corresponding to one eigenvalue, only one eigenvector is there, and the answer, clear-cut answer will be no. This is the no. This is the answer of this question. That means our answer will be corresponding to one eigenvalue, infinite numbers of eigenvectors is there. Actually the answer is corresponding to one eigenvalue. Answer is corresponding to one eigenvalue. No, I can have a no bhabbe. This will be also taken as a no. So actually answer I am giving it at the end of the second page. The answer of the previous question will be corresponding to one eigenvalue. There is infinitely many eigenvector, and this can be easily seen from there that any k2 multiple of minus 1 1 is eigenvector. That's why in eigenvector it is not mandatory that everyone should get a same answer. It is not mandatory. Someone here I have taken x2 is equal to k1 and x1 is equal to that value. Someone may take that x1 is equal to k1, may take it, no problem. So if x1 is equal to k1, so then you will get that 4x2 will be same as x1 is k1 and x2 will be k1 by 4. Someone may get that. In that case, the answer will be x1, x2 will be x1 is k1 and x2 is k1 by 4. So if you take the k1 common here, so you will get 1 and here 1 by 4. So this 1 by 4 is also one type of eigenvector. It is also correct. Then not necessarily that it will be always in the real in the integer form. You may get fraction also as eigenvector in the component. That 1 by 4, because actually whatever I got here, I have taken the, suppose k1 is equal to, if I take something about 4k. If k1 is equal to 4k, then you will get this type of solution. It will be 4 and it will be 1. So that's why if you follow this condition and if it is actually correct in your answer, then whatever maybe you are taking as a assumption, but you can take both as assumption. You can, since nullity is 1, you can take only one and others have to be dependent on that. And whatever you are getting after taking the k1 common, this will be your eigenvector. So this is the way for calculating eigenvector. Someone may got this type of fractional eigenvector also. So it is also permissible, it is also correct answer. And someone may multiply it by 4 to get this type of form, 4 1, it is another. Someone may multiply it by 100. If take k1 is equal to 100, then it will be 100, it will be 25. This is also one eigenvector. But and every of this answer is actually correct answer. But we generally prefer just do it simple. Whatever you are getting, put it as the answer. Okay, so that is the process of finding the eigenvalue eigenvector. Now if you have any question, you can ask, or otherwise we can complete the class here.